Hello, this is Luis Vasquez, and I'm here today to talk with you about a work in collaboration with my doctoral advisor, Thomas Jordan. I would like to discuss on some preliminary results on updating probabilistic earthquake rupture forecasts using earthquake simulators. In 2018, Shaw and others demonstrated that RSQ-Sim could generate similar peak ground accelerations to those obtained from user-3. In this study, we're going to be using long earthquake catalogs generated by RSQ-Sim in order to update the user-3 time-independent model. I will start describing the components of the Uniform California Earthquake Rupture Forecast version 3, and then I'm going to move on describing how RSQ-Sim works and what we can get from it. Then I'm going to describe our Bayesian approach that we use to update the time-independent user-3 rates for earthquakes larger than 7.0 using two different catalogs. One was used for calibration and the other one was used for testing. Each of those catalogs have a duration of 500,000 years. User-3 model provides authoritative estimates of magnitude, location, and frequency of the potentially damaging earthquakes in California. It starts by defining where the earthquakes can occur in the fault models to then obtain the deformation models, or in other words, it provides the fault slip rates. And those two models are the inputs to earthquake simulators, such as RSQ-Sim. We then compute the earthquake rate models, and that will give us the time-independent models, which is the long-term rate of all the possible earthquakes that can happen in the faults, given in the fault models. We can extend this to further incorporate probability models to compute the time-dependent models. It's important to say that our ultimate goal is to obtain time-dependent models, but in this occasion, we're going to be discussing only the time-independent one. The lower plot shows the time-independent forecast from user-3 for earthquakes larger than 6.7. Red colors represent high values for participation rates, and blue colors represent low values for those participation rates. Please notice that the San Andreas Fault and other major faults are colored in red. RSQ-Sim is a physics-based multi-cycle earthquake simulator which captures the earthquake cycle in three different states. State 0 is the inner seismic period, state 1 is the nucleation period, and state 2, which is the rupture propagation period, in which RSQ-Sim allows for stress transfers. It also incorporates the radiant state friction loads to capture the spatiotemporal seismicity clustering. In this case, I generated this animation of 100 years of seismicity for earthquakes larger than 7.0. And we start with this large earthquake near San Francisco, and then we generate all the other earthquakes in this period of time. This is the type of data that we're going to be using to update the user-3 time-independent model. All right, now we have to start with the Bayesian calibration discussion. Please focus your attention in the plot on the left. Observe that there are two different fault models, one in white and the other one in gray. The gray faults are for RSQ-Sim, and the white faults are those for user-3. Please notice that there are differences among them. That's why we need to map RSQ-Sim ruptures into the user-3 event set. In order to do that, we define something that we call the rupture criterion, which is the fraction of any given user-3 fault subsection that was ruptured by an RSQ-Sim event. And we're going to do the mapping process with two goals in mind. One, we want to maximize the number of mapped RSQ-Sim ruptures. And the other one is that we want to minimize the moment bias. And the moment bias is represented by the plot in the middle of this slide, in which we have a scatter plot of the user-3 magnitudes in the horizontal axis and the RSQ-Sim magnitudes in the vertical axis. If we didn't have any moment bias, this scatter plot would be concentrated around the one-to-one line, which is the red dashed line. However, we fitted a line, which is the green dashed line, and that has a slope of around 0.7. We want that slope to be as close as possible to 1. And also we want to maximize the number of dots in this scatter plot. We do that in the plot on the right. We plot the slope of this green line for different scatter plots using different rupture criteria. And that's represented by the red dots. And the lower subplot gives us the number of mapped RSQ-SIM events as a function of the rupture criterion. We chose a value of 50% just because the slope isn't that far from from 1, and because we have a fairly good amount of mapped RSQ-SIM events. It's important to say that we have a moment bias because in general, the RSQ-SIM events have a larger stress drops and also larger fault areas, which will be translated into larger magnitudes, which we can see in this scatter plot. All right, now that we have mapped those ruptures, we adopted a Poisson gamma model to update the time-independent rates using RSQ-SIM. We do that by defining the n sub n variable, which is going to tell us the number of times that RSQ-SIM mapped the mth user 3 rupture, and that's going to be assumed to be Poisson distributed. We then choose the prior distribution as a gamma distribution, and the posterior distribution is going to be also gamma because the Poisson and the gamma distributions are conjugate. We then take the expected value of the rate given in equation number 3, and we ended up with equation number 4, in which we know everything. We know the counts by RSQ-SIM. Capital M is the number of ruptures from user 3, which in our case is 9,090. And the lambda wiggle is just the prior rate given by user 3. Capital T is the duration of our catalog. In our case, is 500,000 years. What is remaining is the value of A, which is called pseudo count. This equation leads us to ask the question, what is the optimal value of this parameter? And we do that in the next slide. We take the calibration catalog to test it against the testing catalog. We do that by taking the negative-oriented logarithmic score for different forecasts using different pseudo counts given in this equation in the red box. We observe that we have really small values of A and really large values of A. And if we have really large values of A, the logarithmic score is going to tend to approach the prior logarithmic score, which is telling us that if A is large, the prior and the posterior are identical or almost identical. And if we zoom in this region of the plot, we will end up with a value of 2 for the optimal value of the pseudo count. We use that value for computing the event rates to, which are represented in this plot. In the horizontal axis, we have the user 3 event rates versus the RSQ-SIM event rates in the vertical axis. We have this red dashed line, which represents the one-to-one line. If the calibration hadn't done anything to our rates, these rates would be the same. These rates would be concentrated along this line. We also have some unsampled ruptures represented by these purple dots. And those are ruptures that could happen at least once every 1 million years, according to user 3, but those are not allowed by RSQ-SIM. If we look at an example of those ruptures, we will see this really interesting rupture, which ruptures the southernmost portion of the South Mojave section all the way down to the Coachella section. This rupture could happen according to user 3, but it is not allowed in the RSQ-SIM simulator. We then take these event rates to convert them into participation rates, which give us the final time-independent forecast. Again, in the horizontal axis, we plotted the user 3 event participation rates, and in the vertical axis, we plotted the RSQ-SIM results. We have the one-to-one line right here, and in purple, we showed the participation rates of the San Andreas subsections. Please notice that these ruptures have the higher values for participation rates. We can further visualize these ruptures into this manner in which we observe the RSQ-SIM participation rates on the left, in which we have the rates for earthquakes larger than 7.0, and they go from 10 to the negative 6 in blue to 10 to the negative 2 in red or pink. we observe that the San Andreas fault system is colored in red, as well as other major faults. If we go to the middle plot, we will have the participation rates given by user 3. We observe that the San Andreas fault system is also colored in red. However, there are differences that are noted in the rightmost plot in this slide. For this slide, we took the ratio of the RSQ-SIM rates over the user 3 rates. And the yellow colors represent unchanged rates. Red and pink colors represent increased posterior rates, whereas blue colors represent smaller RSQ-SIM calibrated rates compared to those by user 3. We're going to be focusing more on the San Andreas fault system in this slide, in which on the right, we have the scatter plot of the participation rates for a few different parent sections of the San Andreas fault system. And we have the one-to-one line, which is represented here in the red dashed line. We observe this cluster in black, represented by the black stars, which represent the participation rates for the Carrizo parent section. And that means that those rates weren't changed after the calibration. And the Carrizo section on the left is represented by this yellow section, meaning that user 3 and RSQ-SIM both agreed on those participation rates. However, we have other examples of changed posterior rates. Like, for example, if we look at the pink circles here, those are for San Gorgonio, of the San Gorgonio section of the San Andreas fault system, and those were decreased, meaning that RSQ-SIM doesn't allow for those many ruptures in that region. And that is just because RSQ-SIM doesn't allow ruptures propagating through the San Gorgonio node all the way down to the Coachella section. That region is colored in blue right here. We also have the opposite behavior, in which the posterior rates were increased. They are above the red dash line here, and those are, let's focus on the blue stars here, which represent the results for the South Mojave section. We also have the North Mojave section there, but they are covered by the South Mojave results. Those were decreased, meaning that RSQ-SIM says that those should occur more frequently compared to what user 3 states. Those results are shown in this section of the San Andreas fault system in the plot on the left. So those are some interesting differences that we can observe by looking at these time-independent forecasts. And to conclude, we were able to map RSQ-SIM events into the user 3 event set by using a 50% rupture criterion. We also were successful to use a Bayesian calibration approach to update the user 3 time-independent rates using RSQ-SIM. And we observed many interesting differences between the time-independent rates given by purely user 3 models and those that were calibrated using RSQ-SIM data. An example of that is the decreased posterior rates of the San Gorgonio section, which tell us a difference between the behaviors of RSQ-SIM and user 3. Without further ado, I'll be happy to take any questions during my live session. And if you have questions or comments, please don't hesitate on contacting me. This is my email and Twitter. And it's important to say that this is a work in progress. We acknowledge that we cannot handle correlation among ruptures, but we're going to simulate those correlations in future studies, including time-dependent studies.